In section 4.6, we're looking at how to solve polynomial and rational inequalities, specifically algebraically, but we're going to use our calculator and do some graphing to kind of help us along the way, give us a bigger picture of what's going on with our expression overall. It offers at the last slide of the PowerPoint a 4-step process. The first step is to have all of your terms on one side. So you want this guy basically equal to 0. So greater than, less than, greater than or equal to, less than or equal to, with 0 on one side. If you want to solve it as a system, you can do that as well using your calculator. Step 2 is that you want to find your solution. So if it were just an equal to, where would the roots be? Where are you going through the x-axis? But also, if you're looking at a rational expression, you have to look at where it is undefined and find those asymptotes. And so our graphing procedures that we looked at a couple of sections back and then also in chapter 3 for polynomials will need to be used. You're going to use those roots and you're going to use those places where you have asymptotes, and you're going to kind of set up intervals. But instead of setting up intervals and plugging in numbers to check for whether they're positive, negative, or 0, we're going to use our calculator to help us out. And so I have my first polynomial inequality that we're going to look at. It's x cubed minus an 81x less than 0. And so what I'm going to do is begin to factor this, because remember, when you have something that is not just linear, your degree is higher than a 1, your really only plan of attack is to hope that it factors as much as possible, so you can use the zero product property. I can factor out an x. I get an x squared minus 81 less than 0. And of course, that's the difference of two perfect squares. So I get x plus 9, x minus 9 less than 0. So I'm going to kind of ignore the less than and say, well, what if it were an equal to? Where would I be going through the x-axis? Because those solution points are going to be the same. So at 0 and at 9 and at negative 9, I'm going through the x-axis. So let's go ahead and put that on here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's my negative 9. 3, 6, 9, positive 9, and then the 0. You should also look for your y-intercept. In this case, our y-intercept is going to be also in the same spot as our x-intercept since we're going through the origin. But if you are looking for a y-intercept, then you're going to let x equal 0, and 0 to the third minus a 0 is still a 0. So I have a y-intercept at when y is 0 also in this situation, but it could also be in other spots, and we've seen that happen numerous times. Using our leading coefficient term, we know that since this is positive, it's going to be heading up from left to right. And we know that the end behavior, because it's an odd degree, is going to be split. So we have something that looks like this. So I have to be coming up, going through the negative 9, turning around somewhere, going through the origin, and then turning around somewhere in here again and heading back up. And so my graph looks something roughly like this. Now, I don't know if the dip down is way down here or if it's way close to the x-axis like that, or if this one's up here or maybe goes up a little higher. But we're not so much concerned about where those maxes and mins are in between. We would need calculus or the calculator to help us out to find those. What we're looking for specifically is where is this function less than 0. So I'm less than 0 here and from here to here. And I don't want to include it. It's not an or equal to. So it's just numbers that when I plug in, they're going to be negative. And so I'm going to be negative from negative infinity as I work my way up to the negative 9, but don't include the negative 9. That's when it's 0. It hits negative 9, becomes 0, it's positive, all the way till it hits 0 over here again, not included. And then from the 0 to the positive 9, it will stay negative, but you can't include the 0 or the 9 because there it's 0 for a y value, and anything above that 9 is going to give you positive numbers. So my solution set of where is this function equal to or less than 0 is from negative infinity to negative 9 or from 0 to 9. We're going to do the same procedure for our rationals. Rationals are always a little bit more involved just because sometimes they break their own rules. First, we'll look for asymptotes. We have a numerator degree of 1 and a denominator degree of 1. And so my horizontal asymptote, because the rule that uses the degrees, is going to be at the quotient of the leading coefficients, which is 1 divided by 1, which is 1. So I'm going to come to y equals 1 and put that in. For my vertical, since I don't have anything that could be factored and then divided to a form of 1, I'm just going to take my whole denominator and set that equal to 0. And that's at a positive 2. Don't have to worry about any oblique because the obliques are only from when your numerator degree is higher than your denominator degree. Now I need to find some intercepts. So where's my y-intercept? That's going to be the easiest because that's when x is 0. That will be at a 4 over a negative 2, so negative 2. So I have 1, 2 down, and there's my y-intercept. Now my x-intercept, that's when y is equal to 0. And so if I set this whole rational expression equal to 0 and cross multiply, what happens every time is that your denominator will get zeroed out because it's like a 0 over 1. So it's going to look like you just take the numerator and set it equal to 0. It's that the 0 during the cross multiply wipes out your denominator. Either way, I get an x-intercept at a negative 4. I'm going to scroll back up, put in my negative 4. And so I have something that kind of looks like this. And maybe something over here. And rationals can be a little sneaky. And so we'll go to the calculator. And we'll type in x plus 4 over x minus 2 and make sure that we're in the right spot. And it looks pretty good. Remember, rationals and even some of your bigger or quicker polynomials are going to be a little bit difficult to see on your calculator, so you kind of have to merge your algebra and your graphing calculator so that you can get a good picture of what's going on. We're looking for where is the curve greater than 0 or equal to 0. So I'm looking for right here up till I hit that negative 4 above 0 or 0. Then after the negative 4 dips under and it stays in that direction. And then once it hits the 2, it pops back up over to the other side. And then for the remainder of the time, I'm above 0. So I'm going to be greater than or equal to 0 from negative infinity to the negative 4 included, because 0 is okay. Remember, if you have a straight bar there, you'll have a straight bar there. Or you can start at 2, not inclusive though, because 2 is not even a part of our domain, to positive infinity. And that is how you do your rational inequality.